Hello, everyone, and welcome to today's webinar focused on power management. While we wait other attendees to log in and join us, I want to introduce myself. I'm Jackie Garcia, and I'm part of the Efficiency for Access Design Challenge team and the facilitator of this webinar today. As a reminder, these webinars are designed for the participants of the Efficiency for Access Design Challenge, which is an initiative led by Efficiency for Access with support from Engineers Without Borders UK. This webinar is being recorded, and the cameras and microphones are disabled except for those of the main speakers, but you all can use the chat box to make any comments or questions for our speakers at any time, and we will be discussing them at the end of the presentation. Now, I would like to introduce you to our speakers today, Venkat Raharaman and David Tusubira. Venkat is founder and CEO of Sidney Energy, a technology product company in the solar DC system and DC microgrids. Venkat is an advisory committee member of National Center of Photovoltaic Research and Education, NCPRE, in India. He has over 20 years of experience in product design and engineering management. Prior to that, he was the CEO of Solaris and Sukan Power Systems, a leading power backup and RE solution provider from India. Earlier to move into the renewable energy space, he was the Vice President of Engineers at Portal Player, a company that was acquired by NVIDIA Corporation in January 2007. He worked at Sun Microsystem, USA, and he has a BE degree from Madurai Kamaraj University and a master's degree in electrical engineering from Stanford University. David is a tech entrepreneur, holds a bachelor degree in electrical engineering from Makerere University. Hardware developer with a background in robotics, currently he is the Chief Technology Officer and co-founder of Innovate, a company based in Uganda with a mission to transforming the distribution of solar grid energy systems and equipment using digital tools, using Internet of Things or IoT technology to promote access to solar energy in sub-Saharan Africa. And now, without further ado, I want to give the floor to Venkat. So if you can unmute yourself, we change the slide.
Thank you, Jackie. Hi. Yeah, thank you for a kind introduction. Thank you so much. Truly appreciate it, Jackie. So, hi, everyone. My name is Venkat Rajaraman, founder, CEO of Sidney Energy. Before even I sort of talk about, I think today's topic is more on power management. I just wanted to understand the audience here. So, Jackie, if it is possible for you to sort of launch this, yeah. So, thank you. So, can I get an answer? I think I just wanted to understand the audience in terms of the basic understanding of power electronics and power management. If you can sort of select one of these choices, that would be great. All the way from, hey, I don't have much of a knowledge, to I am extremely proficient. So maybe that would help us to sort of sort of pace this presentation and also see how much deep we need to get into. Appreciate your response on this. So maybe we have about I think Jackie, maybe about oh wow, okay, fantastic. Okay, thank you so much. So this is the result. So it looks like, I think it's between very little to a basic understanding. So obviously, I think me and David will keep this in mind, and we will make sure that we don't go too deep into the technical side, but at the same time trying to give you a overall big picture. Hope you find that useful, so we can get back to our slides. Thank you. So next slide, please. Got it. So a very brief introduction about Sidney Energy. We are incubated at a research institute in India by name Indian Institute of Technology, Madras. So the focus has been on a combination of solar storage and energy efficient appliances. We have been sort of working on the solar DC technology for over 5 years. As Jackie mentioned, we have also done some DC microgrids, working on the DC bus architectures. We have also done quite a few projects based on these DC installations in India, and we also worked with the standardization body in India called the Bureau of Indian Standards to standardize the LVDC standards. We are also working with both IEEE and IEC for standardizing the DC standards. We also raised some money as part of our growth, and one of our microgrid project also got awarded the best project in the microgrid conference last year in San Diego. Next slide, please. Okay, so let me talk about Energy 2.0. Some of you may be aware, some of you it may be a new information. I just thought I'll talk about this. All along the energy over the last 100 years have been sort of going in such a way where you had large centralized power stations, thermal coal-based power station, and then you have these transmission lines which cover hundreds of kilometers. And then there is a last mile distribution before it reaches our homes, offices, industries, and so on and so forth. Now, this paradigm of energy generation, distribution, and consumption is going through a sea change. It's going through so much change in the last 5-10 years that this industry that had not seen in the last 100 years. Some of the changes that are happening is, one, there is a decentralized generation, right? More and more of generation happening closer to the consumption is happening. There is also a lot of decarbonization, right? There is a lot of generation which is happening through renewable energy sources, through solar, wind, and so on and so forth. And this is clearly resulting in the disruption of this industry itself, right? There are new business models, there are new technologies, there are new ways and means of generation and the consumption of energy is happening. This also results in democratization of energy. For example, there used to be a utility provider before who used to charge the end consumers. Now, we are talking about peer-to-peer energy transfer, energy trading, and there are multiple energy as a service providers. I'm sure the folks who are on this call may be well aware of that. And the other most important thing is happening is energy and communication. They are transforming into one, right? The digitization of energy, as we call it, energy as a service, where a lot of telecom operators now coming into energy. The folks in sub-Saharan Africa can fully appreciate this, where the energy is coming as energy as a service. All of them are transforming this energy domain as we know it, and I'm going to be talking about this in the next few slides and more in detail about what these transformations are. Next slide, please. Yeah, so the second one that I want to talk to you about is something which is close to my heart. This happened more than 100 years back. Some of you may have seen this War of Currents, which is a great this thing in the National Geographic Channel, which happened between Dr. Thomas Alva Edison and Dr. Nikola Tesla more than 100 years back. If you look at it, now 100 years later, I think it looks like it's coming a full circle, where lots and lots of appliances are moving towards what is called as direct current energy efficient appliances, right? So if you look at in our homes and offices, about 15 years back, all of our mobile phones and computers were all DC for quite some time, for more than 2 decades now. And about 10-15 years back, our lighting is all changed into LED based lighting. Light emitting diode is a DC based lighting. So the lighting has moved to DC. All the water pumps now are moving towards DC based one, and of course now you have refrigeration and air conditioning towards the DC one, and an entire thing spectrum is moving towards the DC. Given all of them, what happens is you are seeing the DC adoption everywhere. You see a DC adoption in electric vehicle, which is the biggest driver for DC. You also see DC in the grid level energy storage. You see DC in the microgrids. You see DC in the solar water pumps, and of course DC in the productive appliances, which we'll talk about it in the coming slides. And of course there is an hybridization of both an alternating current and DC current coexisting in many of these kind of installations. Next slide, please. Next slide, please. Thank you. Yeah. So I think the slides are slightly this thing. So can you please go back to the previous slide? Maybe. Ella, thank you. Yeah. So I just will take the slides have not come out well, but I still sort of will talk about it today. If you have a traditional solar system in your home or office, what happens is you have a solar panel on your rooftop. And you need to have a storage because the grid is not available 24/7. So when you have a storage, when you have a solar, what happens is you have the solar inverter, which is nothing but converting this DC power which is generating from the solar panel into an AC one. Similarly, if you have a storage, then you have a battery charger and an inverter which does nothing but a DC to AC and AC to DC conversions. And as we have seen in the previous slide, many of our appliances are moving towards DC, and in almost all the appliances you have a front-end converter and an adapter which does this AC to DC conversion, right? So in all of these places you find that every time there is an AC to DC or a DC to AC conversion, you lose power, right? And this is what we decided to do was we will completely move towards the DC, so that the DC power from solar panel, DC power from the storage will directly drive the DC appliances, and you have one high efficiency converter on the front, so that you can directly sort of you can optimize, because of which what we saw was that you could save about 45% of your energy, which is basically getting lost in a conversion loss, can be saved by this approach. Next slide, please. Yeah, so this is what we had done. So the product what we have is what we call it as an inverterless product. So this product takes the power directly from the solar panel. It also has an interface to the grid as well. The product gives you both the DC power as well as an AC power. AC power for a traditional AC appliances that may be there in homes and offices. The DC power drives all the electronic DC appliances, be it is computers, be it is televisions or a lighting or a fan or any of the motorized load, directly drives that. And they are all sort of connected through the mobile app, so that for both monitoring and control can be done. Which is what we have done as part of our this thing, and I thought I'll basically talk about it in the next few slides in terms of what we have done. Next slide, please. Yeah, so this is the product portfolio. I will not delve deep into that for want of time, but so we have this. These are all of these devices are hybrid AC DC devices. So it takes in the battery in most cases is built in here. It takes in the grid power where and where it is available. It takes in the solar input, and in most cases it can provide you both a DC output as well as a DC output. So this is a 1 kilowatt system, and the ones on the right hand side can go all the way up to, it starts from 2.4, 4.8, 7.2 kilowatt and multiples thereof. So you can even have a 10 or a 20 kilowatt microgrid using this, where you sort of it's a modular in nature. All of them comes with an IoT with remote monitoring, which I am sure David is going to be talking more. Next slide, please. Yeah, so the biggest use cases what we saw were that is for the productive appliances. See, today, the lighting problem, the problem of running maybe a mobile charger or a fan, it is well addressed. There are several dozens of companies in South Asia and Africa which are already doing it. But what we found was an interesting application was to run higher powered appliances. Whether it is to run. So the instrument, the equipment, what you see here is a textile power loom, right? So that you can actually make your clothes with that. And this is the the solar electric cook stove. This is for the milking unit, for weighing of your for the dairy industry. And this application is towards a dairy, towards for fisheries, for cottage industries, for horticulture. All of them, this can be used, because this comes under the slightly higher powered one. What I thought, instead of sort of talking about it, I'll show you a short video. Maybe I think you will find that more useful in terms of what we are trying to do. Next slide, please. Is there an audio on this, or can the audio be enabled? Jackie, I still don't get the audio. Doesn't matter. I'll talk through this. Maybe the audio is.
Let me try another thing to share the video.
Okay.
Just give me 1 second.
Sure. Yeah.
We cannot hear you, Venkat.
Got it. Thank you so much. I was speaking, but I didn't realize that it had gotten onto this auto mute. So thank you, Jackie. So I was saying that this is a great example of the system powering a power loom. Countries like India alone has a 2.8 million of these power looms. What you saw, these are all typically in places where the grid is either not available or the grid is weak, and almost all the time the folks are dependent on a diesel generator. There are two problems. One, carting the diesel is a problem, and it's very highly polluting, and it's very expensive as well. So that's where we sort of are using this for productive appliances, mainly from a power loom. I have one more short video, Jackie, if you can play that, please. Thank you, Jackie. Thank you. So this is the second one is for a freezer or a chiller application. Again, the applicability is huge. One can use it for a dairy industry to store, for example, milk or any other beverage. It could be used in, pharma for storing of the medicines and other stuff, and it can be used for storing. So, we are also seeing that this is all of them are now powered by this higher capacity appliances. So next slide, please, if you can go to the next slide. I think I have 2 more minutes, and then maybe I'll try to wrap it up. Maybe. So now the extension of that, so the DC microgrid, what we have also done is this box now, for those places where if you want to run a small tiny grid, let's say for example 4 or an 8 or a 12 home, what we have done is we have also come up with this small sort of device which can actually measure the power that goes into each home, and if the home draws more power, it will do the power control as well, and all of them are done through the power line communication. I'll not get into the depth of this technology, but the advantage with this is it avoids running additional communication line, and it's communicating on the same line on which the power is going. Next slide, please. Yeah, last 2 slides. Now, the evolution of that is the microgrids themselves. So today, if you look at a traditional microgrid, which are available, in all the places, in South Asia as well as in Africa, they are all AC microgrids. What happens is you have a solar inverter which converts this DC to AC, and then you have, for example, other renewable energy sources. For example, if there are a wind or something, that again gets converted into an AC power. And you have a storage where the AC to DC conversion happens. And then when it goes into the end usage, whether it is for electronic gadgets, whether it is for lighting, whether it is for your computers and so on, again, there is one more conversion. So all the places what you see as in red in color, 2 things are happening. One, there is a conversion happens, and number 2, you are losing about 4 to 20% of the power in these conversion losses. Whereas in the DC microgrid, what happens is you do not do any of this conversion. You take the power in its native form in DC and try to run all of your appliances directly in DC. You do one high efficiency conversion from the grid. The advantage of this is the system cost comes down by about 20%, right? Because you are able to sort of save on this conversion cost, where in several scenarios, this turned out to be a lot more beneficial than the traditional AC one. Next slide, please. Yeah, again, so this basically talks about all these conversion losses that are happening. So if you see on the graph or the, this bar graph on the right-hand side, when you do an AC microgrid, of course, the power consumption comes down significantly because there is a solar. But when you go for a DC with the energy efficient appliances, your power consumption also comes down, and overall power consumption also comes down because you are going in for energy efficiency, which is what we have done in few of our projects. Next slide, please. Yeah, so this is the always on microgrid that we have done. The advantage with when compared to the traditional microgrid is you can actually guarantee almost like a 24/7 power. But for want of time, I will not get into the details of what we have done here, but I'll just talk about one project that what we have done. Next slide, please. Yeah, so this particular one, again, this is the 50 kilowatt DC microgrid with storage and a microgrid controller that controls all of them, and these are all the loads which goes there. This is where we have done, where we provided this always all functionality, which is a patented functionality, what we have done, and this makes sure that even when solar is not there, when the grid is not available, when the battery is, SOC is coming down, it will make sure that there is a 24/7 through which you can provide a quality of service to the end customer. Next slide, please. Yeah, so this is one such project we have done. This is in, this is the actual building what you see in, in the research park in Indian Institute of Technology. So this is a 1.2 megawatt of solar panel on the roof. The entire distribution of this happens at a DC, 2 levels of distribution. One level happens at 380 volt, and the other level happens at 48 volt. And all the appliances are all energy efficient appliances at 48 volt, including the air conditioners which are run. And here we are giving an option where the client who are there have an option to completely get rid of the diesel generator, and they can get the power directly from solar. But I think that's a sort of overview of this project. Next slide, please. Yeah, so this is the concluding style. The message that I want to leave all of you with is there are three global trends that I want us to sort of be aware of. One, there is a huge energy efficiency which is happening, what we saw, because of which your consumption of power in all of these appliances are coming down. The second, there is a significant drop in the PV panel prices as well as the energy storage, through lithium-ion battery and so on. The third one is there is a huge push towards electricity access as well. All three of them are driving this low voltage DC. And what we believe is that the future of tomorrow is sort of going to be, more and more of this, renewable energy, more and more of energy efficient appliances is what is going to drive that. I think with that thought, I'm going to sort of end my talk here. What I wanted to leave you with, if we can have the second poll, Jackie, I just wanted to understand audience feedback in terms of correct. Thank you. So the question is, how many of you think that the direct current will play a pivotal role in providing not only energy access but also livelihood and this thing to the sub-Saharan Africa and South Asia? Again, you can go from all the way saying that I don't think so to you definitely believe so, but I think it would be great to get your feedback. Oh wow! Thank you so much. So I think I think this thing is we are saying definitely believe this is almost about 40%, and I also believe that the AC and DC will coexist for some time. I think thank you so much. I think your feedback is absolutely wonderful. Thank you, Jackie. I think what we will do is I think towards the whenever we are ready, we can take questions at whatever appropriate point of time, Jackie.
Thank you very much, Venkat. And yes, please, everybody, share your comments and questions on the chat box, and we will launch them to our speakers at the end. So now, if we can move to the second presentation. David, the floor is yours, so you can switch on your camera and your microphone.
Hi, everyone. Thank you for the introduction, Jackie. I'm happy to be here. Let's go to the next slide. Okay, so Mr. Venkat already talked about power management and power management within the system. So he talked about the importance of minimizing conversions because there's a lot of loss from conversions. So I'm going to go deep in, I'm going to go to the other side of how can we use data from solar systems to basically tackle the same issue, which is power management. But before I do that, I'd like to introduce my company, Innovate, Uganda Limited. So Innovate started in 2015. We went commercial in 2017. Our core business is the development, manufacture, and production of IoT technology that is used for monitoring of PV solar systems. And so this IoT, there's IoT hardware and there's a software platform. The IoT hardware is installed together with a solar system or an off-grid solar installation. And the device will measure data from the solar system, like voltage, current, upload it to our cloud platform where the data can be used to do all kinds of things. And of course, we are also involving a lot of analytics to deal with the data and come up with some useful insights. We have over 1,000 IoT hardware devices out there in the field, around 5 countries within the Greater East African region. So next slide. Right, so when we're talking about power management, what exactly are we looking at, and why are we even looking at power management per se? So in my presentation, we're going to look at the major concerns regarding power management. We shall also look at the key aspects of power management on off-grid PV solar systems, specifically pertaining to use of data. And we shall also be looking at how that data can be leveraged to address the key aspects of power management in off-grid PV solar systems. Next slide. Right. So the key concerns, the things that we're concerned about regarding power management are just two, in my perspective. That would be the cost and the return on investment, right? Now, of course, you can argue that these two are one and the same, but just to distinguish them, when you're looking at costs, you're looking at how much does it cost me to get a solar or an off-grid solar solution that will give me a certain amount of energy, yeah. And the return on investment is, am I really going to get my money back? If I were to use the utility grid, how much money am I going to spend over a certain period of time? And if I invested in a solar system, will I get my money back, and how long will it take? And is it cheaper than using the grid? So those are the two concerns regarding power management. Of course, there's the concern of, okay, are we wasting energy and all that? But I think these are the key concerns with anyone who is looking to acquire a solar system or looking to solve a problem by having a solar solution. Next slide. Okay, so what are the key aspects of power management? So one, I would say, is conversion efficiency, and this is something that Mr. Venkat has already tackled by looking at how much energy or how much power you lose by converting from DC to AC and vice versa. You realize that that's costing you power and energy. So conversion efficiency is key to power management. The other key thing is usage, or some people like to call it consumption. How is the energy used? How is the power from the solar solution or any renewable energy solution used? How is it consumed? And the other important key aspect is the system sizing and the system design. Everyone who goes out to get a solar system or a solar PV solution obviously is trying to solve a problem, right? They're trying to fill an energy need, but that comes with the solar sizing. You can't get any kind of solar system. It has to be a particular size, and of course that particular size will have a particular cost. So these are the key aspects that I'm going to discuss. We're going to go deep into each of these and look at how each of these actually factor into power management. Next slide, please. Okay, so with conversion efficiency, on a typical PV solar system, you're going to have conversions. The first conversion is, of course, converting the sunlight or the radiance to actual PV power, voltage and current that comes out of the solar panels. Then the other conversion is that PV power being converted into actual battery charge. This is something that happens between the charge controller and the battery. And then the other conversion would be converting battery charge to the output power, which could be DC power straight from the battery, which would be the most efficient, or it could be AC power through an inverter. Lastly, the other conversions that occur, of course, are happening within the appliances. When the power comes out of the battery or out of the inverter, it is obviously not used as electricity directly. It is fed into an appliance in which it does the work. So this could be a maize mill, this could be a solar water pump, or a solar a fridge. All these, so you're getting cooling. So there's obviously a conversion. Okay, so you realize that in just one small solar system unit that you have in your home, you have all these conversions happening from the solar radiance to how you're utilizing this energy. Next slide. usage. So it's very important to look at how people use power. From my experience, looking at how people use their solar systems, because we have about over 1,000 devices out in the field, and sometimes we get to look at the data. And we have some of our clients running projects where they assess the consumption of this, how people are using the solar systems, what is the loading profile like, and you'll realize that when you and also I've done a bunch of field visits, and you realize that there's a lot of negligence and oblivion, and these all constitute solar system misuse. So one of the instances would be you could install a solar system of a certain size, maybe a 100 amp hour battery or a 200 amp hour battery, and you say, oh, this solar system has been sized for lighting, only lighting. That is interior lights and maybe security lighting, right? And if you do this installation and you visit a few weeks, months later, you find that the battery died because these guys actually tried to put a DC flat iron onto the solar system. Or you'll find that you will hear a call from the customer, the end user, saying, this solar system installed for me is no good because I'm unable to connect my fridge or whatever. So the first thing is, end users of solar systems sometimes do not know the limits of these solar systems, so they will not know how to appropriately use them, right? Sometimes they know, but they just want to maximize it, so that could be negligence, and sometimes they really don't know. So these are the two aspects of usage that affect power management. The other could be the fact that, of course, you do not know what's going to happen tomorrow. The sun doesn't shine every day. So if your solar system is designed with only one day use, and say the sun shines today and you use up all the energy by the time you go to bed, tomorrow if the sun doesn't shine, you're not going to have any energy. So that means you didn't use the system well, but then that's probably because you don't know what's going to happen tomorrow. So these are all things that these are all factors that go into solar system usage that affect how efficient or how effective the solar system is going to be. Next slide. Solar system sizing. This is probably the most it is definitely very important. And like I already mentioned, the sun is inconsistent. The sun is not going to shine every day, and even if it shines today, it might be partly cloudy day, right? Now, you could design a solar system with several days of autonomy, which means that you want, say, your solar panels and your batteries to be able to capture enough energy for even 3 days, right? The problem with that is that it eats into your budget, because you're now oversizing the system, right? You're oversizing the system because you want to have energy available. And when you oversize the system, of course, what happens? The cost goes up. The cost goes up, and because you have very big batteries, and you know how delicate batteries are in regards to maintenance and durability, your return on investment is also going to go down, because you don't know if you're going to really maintain these batteries properly and have them last as long as they should. So with panel array oversizing, you'll find that because your panels are so big and you're generating so much energy in one day, because you designed for several days of autonomy, the next day, if the sun shines, there's a lot of wasted energy from the panel. Okay, so you're wasting energy because you have these large panels, but your batteries are full because the sun has been shining consistently. So there's wastage there. Of course, oversizing the battery, like I already mentioned, that of course increases the cost of the solar system and reduces the return on investment, because batteries are very, very hard to maintain. So you find that solar sizing is something that's very important with regards to power management. And with power management, what you want is the smallest possible solar system for your needs, because that is going to help you with the return on investment and the cost, because the cost is going to be lower, and you're going to have a lot of and you're going to have all the energy you need. So that's really it about solar system sizing and how it goes into power management. Next slide. Next slide, please. Oh, thank you. So how does data factor into these key aspects that we just talked about? Now, like I told you, at Innovate, where we make IoT technology, and if you look at this image, you can see the values that we're able to collect from the solar systems. So the kind of data that you want to acquire from the solar system in order to assist with power management is something like you might want to get irradiance data. You want to know how much energy is the sun actually producing. Okay. The other thing you might want to know is what's the weather forecast. What is the sunshine going to be like tomorrow and the day after? You also want to know how much power your panels are producing every other time. You want to know what battery charge you have left in the battery, and of course, you also want to know how the energy is being consumed, either from the battery or directly or through the inverter. This is a very important information to capture because it helps in optimizing the usage of the energy going forward. And of course, how you can acquire this data is through the Internet of Things with data loggers, like the kind of hardware that we produce at Innovate. Next slide, please. So now that you have all this data, okay, so let's say you're able to collect all this data. How exactly does this data help you do power management? So one example is remote switching. A lot of solar systems, the vast majority of solar systems, at least I can speak for Uganda, are for lighting, okay? Which means that these people only use the energy during the night, basically. Now, our IoT hardware has a function where you can set a timer where you say that you want all the loads to be off during the day from 6 a.m. to 6 p.m. and you want to allow the loads to be on between 6 p.m. and 6 a.m. That's the entire night time. So this is functionality. This is the IoT functionality that we've implemented, and it's very, very beneficial because you realize that with end user negligence, people will have lights on during the day when they actually don't need them, and hence they'll be losing energy. You know. The other thing is with this data, you can actually compare different components. So, like we mentioned with conversion efficiency, there's so many components in the solar system, and there's so many conversions happening. But different components have different efficiency. And if you want to identify what kind of solar components have very good efficiency or perform well, or how do you size solar systems to make sure that you're having the best efficiency? Because you realize that some inverters have, if not all inverters, have different efficiency for different power, percentage of power that you're using. So if an inverter is, say, a 500-watt inverter, if you're using 450 watts, the efficiency could be 95. When you're only using 100 watts on a 500-watt inverter, the efficiency could be much less. So you want to know these things. And how will you know these things? By looking at the consumption data and knowing, okay, this inverter works better, this inverter has a better efficiency at this time, or in this condition. So by looking at the data, you can identify which solar components work best or give you the best efficiency or performance, or save you the most energy. The other thing is usage influencing through notifications. So an example is on our platform, we do send end users notifications based on how they're using the system and maybe what could be the forecast. So for instance, if a home, if it's a solar home system, and people typically use the power a certain way, you can actually map out that usage pattern. And if you know that the forecast says that tomorrow is going to be a cloudy day, you can notify these people today before the day ends that tomorrow is going to be cloudy, so use your system sparingly so that you can have energy tomorrow. So usage influencing, which is informed by the data from consumption and weather forecast, will also help people use their solar systems better and help with power management. And applying data to solve the power management problem, of course, will have efficiency increase. And with efficiency, again, what we're looking for is how can you get the most energy or power or reliability from the smallest possible solar installation at the lowest cost with the highest possible return on investment. Yeah, I think that's pretty much what I had to share. Thank you very much. The next slide is my contact. Thank you.
Thank you very much, both of you, for your excellent presentations. I hope the attendees have enjoyed as much as I've done and learned something new today. And now I would like to open the floor to questions from our participants. So please share your questions to our speakers on the chat. First question, it's about what's the way to go for countries with low irradiation, especially those far from the equator. Also, if you can switch on your cameras, David and Venkat, it will be great to see you while you answer the questions. Thank you. So who wants to take this, or both of you?
Yeah, maybe I can go first, and then see today, the solar irradiation, right? Though you may be, for example, one thing one has to realize is you need photons for the solar to generate, right? One does not need a bright sunlight, or one does not need very high amount of irradiation for the solar panel to generate. That's one of the reasons, for example, in India, the Himalayan regions of Jammu and Kashmir, right, the Leh Ladakh is considered one of the best places for solar installation because the temperature is low, but at the same time you have sufficient solar irradiation. So having said that, one has to take care of issues like snow, issues like how much of weight the solar panel can handle under such extreme weather conditions and so on. But it has been proven that many of these countries even far away from equator, solar does work. And of course, one has to slightly size the panels more so that one gets the extra power which is required. The benefit of this solar panel the pricing has come down by tenfold, right? What used to be at $2 a watt peak now is less than 20-25 cents, right? So it's essentially there is a significant drop. Because of which also the additional capacity is doable. So that's my take. So solar is definitely even in these places far away from equator, one can use solar actually. David, do you want to add something?
Yeah, I very much agree with you, Venkat. I think it's really about the panels. I do think that, of course, in those regions farther from the equator, they have to spend a little more on the panels because they need slightly bigger panels, but the panels are not the bulk of the cost in the solar system. And solar panels, the price of solar panels has been, even though the efficiency is not going up fast enough, but having a bit more panels doesn't have a very large impact on the overall cost of a solar PV system. So it's not too much to worry about.
Thank you for your answers. Are DC systems safe, and what kind of protection system one needs to have in a DC system to make it safer?
Yeah, Jackie. So DC system, the good news is they are inherently safe. They come under what is called as SELV standard, which is safety extra low voltage standard. So anything which is under 60 volt, they are deemed safe by all the agencies, which is IEC and IEEE. The other advantage with the DC system is the protection systems have also sort of fairly evolved over the last 5-6 years. There are DC MCBs, there are DC surge protection devices, and so on, because they have been used in the solar industry. Solar industry, for many of you may know, the DC voltage goes all the way up to 1000 volts, and there are sufficient protections which are already available. The good news is the LVDC standard that I talked about, that comes under the SELV standard, the safety extra low voltage. And this is also now recommended by IEEE as part of their P2030 standard. Of course, one has to limit the per circuit current to 10 amperes and so on. But the good news is they are safe, and one can easily operate LVDC without worrying about the safety aspect.
Thank you.
For me, I don't have an answer to that question, because I think Venkat is more qualified to answer that. Actually, I have a question for him. I have a question for you, Venkat.
Yeah.
You said that you talked about low. Of course, we understand that DC is typically low voltage, and of course less harmful, far less harmful than AC. I mean, this was the fight between Thomas Edison and Tesla. But you talked about the DC mini grids and microgrids. How do you get? We know that DC has a low voltage. You have a voltage drop issue. How do you address the voltage drop issue with the DC microgrids and mini grids?
A great question, David. What we do in the microgrid is there are two distribution voltage we do. One distribution happens at a 380 volt. I did mention when I was giving that DC microgrid example. There you can actually run this at 380 volt, very similar to what happens in a grid connected solar system, right? The DC voltage runs at that voltage, and then towards the very end, when it is reaching the end consumers, homes and offices, we drop it down to 48 volt and power the appliances. So you take care of that by running this at the 380 volt DC. Thank you for the question.
Thank you. There is another question. What do you see is the role that product or appliances design can play in the increase of households' income and the interlinkage with the power management to enhance this?
Should I go on that, David? Yeah. So
yeah.
So I think that's till about few years back, household was predominantly focusing on lighting and focusing on maybe some level of comfort with cooling and so on, right? So today, with the increase in sort of a disposable income, there is a general trend towards more appliances, right? People are looking at freezers or refrigerators for keeping their produce. Folks are looking at televisions for entertainment. People are looking at having a computer for gaining their knowledge. So there is a whole thing which are happening. And in the process, what happens on a power management side, many of the solutions which are now coming out are fairly modular in nature, right? So you start off with a very small, maybe about a 50-watt solar home system. But I think as the aspirations increase, they would like to see how do you go from a 50-watt to 100-watt, 100 to 150, and then how do you add on more appliances so that one can gradually sort of increase that. And many of the newer systems support that, including, and the belief is that at some point of time in future, the grid may come in. At that point of time, you really do not want to throw away the solar home system. So you need to seamlessly integrate. So many of the new systems also allow that to happen so that you have grid integration, you have a modularly, you can increase that, and you increase more of these energy efficient appliances.
Thank you.
I think Venkat got that, so yeah.
You are experts on power management and solar systems, but do you know if there are any other energy sources that could be used to power off-grid appliances apart from solar energy? And are those commercially viable? And if not, what will be needed for this to happen?
Wow, great question. Yeah, so I don't have a great answer, but let me try answering that, Jackie. So today, for example, you look at a solar system, you are able to get this at a price which is lower than the cost of the grid itself, right? So many places, the cost of solar, power is lower than that of the grid for the end consumer. So which means that is there any technology today which directly competes with solar? I am not able to think of right away, right? So there are, for example, smaller windmills which are there one can use. There are also sort of smaller biomass energy systems that one can use for their homes and offices. But at a scale which is there, and as well as at the proliferation that solar has seen, I had not seen any other technology coming close to that at this point of time, actually.
I think in my case, in Uganda, the only technology the only other source of energy outside solar that people have tried to use is biogas. It's the only one that I've seen that can generate a decent amount of energy, but that's also not very common. So I would say it's very, very hard to compete with PV solar. Very, very difficult, and it's a tough question.
Thank you for your answers to a challenging question. We are running out of time. I want to thank you for your time, for being here as speakers and presenters, but also to all the attendees. But we have a couple of minutes if you have, if you want to share your final words with the audience today.
Yeah. So hey, I will, I will share my, if somebody wants to get in touch with me, write to me at venkat@sidney.com, cygni.com. We are also, I think there are a lot of students who are there. If anybody who is interested for your, for your project work, I don't know how it works, but I guess that there are folks all the way from South Asia and from Africa. If anybody is interested in your internship, doing a project and all, please reach out to me, and then we would be happy to see if there is an interest and then take it forward. Thank you, Jackie.
I'll say that there's still a lot of problems to solve in the renewable energy space, even specifically within solar PV. And I mean, at Innovate, we try to solve a bunch of them. And so, if you're watching this or listening to this, we have a long list of problems to solve. We have a long list of work for interns to do here at Innovate, and we have a lot of ideas about innovations and different things that you can try in trying to increase the efficiency of renewable energy. So my contact, I think, is accessible. So I would also be happy for anyone to reach out regarding a project or internship, or even bouncing ideas around innovation in the renewable energy space.
Thank you very much again. And now, just want to share that once the webinar is closing, you will have a pop-up window for you to give us your feedback about the webinar, because that will help us to improve for future webinars. It will take you no more than 1 minute to respond. And at this point, just want to remind you that a recording of this webinar will be available on the Efficiency for Access Design Challenge website in case you want to revisit some of the examples and interesting information you've listened here today. This week, we have a series of webinars on different technologies, and the next webinar will be focused on refrigeration, where David Ayal, that is one of the refrigerators that you saw in one of the videos of Sidney, it will be presenting together with Naemeka from Coal Hubs. So hopefully see you tomorrow in our next webinar. Thank you very much for being here today again.
Thank you so much. Thank you so much, everyone. Bye-bye.
Thank you. Bye.